Find the four second-order partial derivatives of the following function. F of xy is equal to the natural logarithm of 5x squared plus 8y squared plus 8. So before we get started here, we'll do a quick little reminder that if we let u be a differentiable function of x, then we know that if we have a function y is equal to the natural logarithm of that function u, then the derivative y prime is equal to the derivative of the inside u prime all over the original inside u. So that is a friendly reminder of our natural logarithm rule from Calc 1. So here, in order to find those four second-order partial derivatives, the first thing we need to do is find the first-order derivatives. So find the first-order partials. And we have two variables here, so we'll have two first-order partial derivatives. So our first one would be the partial derivative of our function with respect to x. We can rewrite this as f sub x. So we have the derivative of the inside of our logarithm here with respect to x, which leaves us with 10x, and that's all divided by the original inside, which is 5x squared plus 8y squared plus 8. And there's nothing we can do to simplify that, so that is our partial derivative with respect to x. And then similarly, we have the partial derivative with respect to y, so f sub y. So here again, we want to keep in mind if we're differentiating with respect to y, we treat x like a constant. So this is the derivative of the inside with respect to y is 16y, and that is all divided by the original inside, the original argument, 5x squared plus 8y squared plus 8. And again, there's nothing we can do to simplify this. So here is our partial derivative with respect to y. So these are the first order partials. So now we want to take these and we're going to use them to find the second order partials. So we'll have 4 total here. And again, just a friendly reminder that from the first orders, this is how we derive the second orders. So from the partial derivative with respect to x, we can attain the second order partial of x with respect to x. We can attain the second order partial with respect to y, so f of x sub y. And similarly with the first order partial with respect to y, we can find the partial derivative of y with respect to x and the partial derivative of y with respect to y. So these are the 4 second order partials here. And a great way to check your work is that these two mixed partials should be equivalent. So the partial derivative, the second order partial of x with respect to y, should be equivalent to the second order partial of y with respect to x. All right, so now that we've refreshed our memories, let's give it a go. So starting here with the partial derivative with respect to x, if we wanted to find the partial derivative, the second order partial of x with respect to x, we want to notice that in this first order partial we have 2 x's. We have one in the numerator and one in the denominator. So you can either use a quotient rule or a chain rule. So I'm going to use the chain rule here. I'm going to rewrite this expression as 10 times x multiplied by 5x squared plus 8y squared plus 8 raised to the negative 1. So in rewriting it like this, I can see the product of the two x terms. So now we're going to differentiate by the chain rule and the product rule. So I'll keep 10 on the outside here. So we have 10 multiplied by the derivative of x is 1, multiplied by 5x squared, plus 8y squared, plus 8 raised to the negative 1, plus x, and then this is multiplied by the derivative of the second term. So we'll have x multiplied by negative 1, hold that inside constant, 5x squared, plus 8y squared, plus 8 to the negative 2, and then we need to multiply this by the derivative of the inside with respect to x, which again is 10x. And so let's rewrite this so it looks a little bit nicer. We have 10 multiplied by 5x squared plus 8y squared plus 8 to the negative 1, and then this will be minus 10 times x squared multiplied by 5x squared plus 8y squared plus 8 raised to the negative 2. And we could continue simplifying this, making those negative exponents positive if we want, getting a common denominator, but we'll stop here for now. This looks good to me. So now again, using this first order partial with respect to x, we need to now differentiate with respect to y. So making sure we have enough room here. We have the second order partial of x with respect to y. And again, we're going to be using this form here because we can see there's that 1y. So we're treating x like a constant here. So we can keep that 10x right on the outside. So we have 10x multiplied by negative 1 times 5x squared plus 8y squared plus 8 raised to the negative 2 and multiplied by the derivative of the inside with respect to y, which is 16y. And then just rewriting this so it looks a little bit nicer, we'll have minus 160 xy multiplied by 5x squared plus 8y squared plus 8 raised to the negative 2. And that is our second order partial of x with respect to y. So keep in mind, we're going to use this as a checkpoint. We want to know, is this going to be, in fact, equal to the partial derivative of y with respect to x? So let's do that one next. So for these last two partial derivatives, we are using the partial derivative with respect to y. And again, keeping in mind how we differentiated for these first two, I'm going to rewrite this as 16y multiplied by 5x squared plus 8y squared plus 8 to the negative 1. All right, so we're differentiating this partial derivative now. All right, so here we go. We have the partial derivative of y with respect to x. So we're differentiating with respect to x here and applying the chain rule. I have 16y on the outside multiplied by negative 1 times 5x squared plus 8y squared plus 8 raised to the negative 2 multiplied by the derivative of the inside with respect to x. So we have that's multiplied by 10x. And then simplifying here, multiplying the two constants together, 16, 10, well actually 3 constants, we have this negative 1 there as well, which leaves us with minus 160 xy multiplied by 5x squared plus 8y squared plus 8 to the negative 2. And we're getting excited because we see that this matches our previous answer. Woohoo! So that's a great sign. Those two are equivalent. And then last but not least, we need to go ahead and find the second order partial of y with respect to y. So again, we're going to need a product rule with a quotient rule. Excuse me, a product rule with a chain rule. Because we can see, again, looking at the partial derivative of our function with respect to y, we can see we have two y's in this expression. So here we go. I'm going to keep that 16 on the outside here. So I have 16. The derivative of y is 1. So we have 1 times 5x squared plus 8y squared plus 8 to the negative 1. And that's plus y multiplied by the derivative of the second term. So that's where we get, bring that negative 1 down. Hold your inside constant, 5x squared plus 8y squared plus 8 raised to the negative 2. And then multiplying by the derivative of the inside with respect to y, we get 16y. And now we need to just rewrite this to simplify. So this is equivalent to 16 multiplied by 5x squared plus 8y squared plus 8 raised to the negative 1 minus 16y squared multiplied by 5x squared plus 8y squared plus 8 to the negative 2. And that is our beautiful final answer here. So these are our 4 second order partials. We have the second order partial of x with respect to x. We have the second order partial of x with respect to y. Actually, I have them labeled here. And it's equivalent to the second order partial of y with respect to x. And then last but not least, we have the second order partial of y with respect to y. Phew! So there we have it.